All right, so hello everyone. My name is Davy. I'm working under Dr. Carde, and we're working on a cascading failure analysis for ocean energy turbine generator arrays. And if you don't understand what that means, that's okay. I will explain it. So the SNEMREC RUs, we're all working on projects that are related to these ocean current energy turbines. And my project takes a bit more conceptual and futuristic approach. We look at what happens whenever you have large arrays of these turbines. Right now, we're still in the single turbine testing phase, but my research wants to know, once we have a large array of these, that's what you need to power a city. You can't just have one turbine out there. So eventually, commercial, manufacturers are going to be looking for this research. They want to know what happens when you put a lot of them together. And when you put a lot of these turbines together, you're going to get a very complex system. It's going to be much more difficult. They have different problems that arise whenever you start connecting these things. So it's also interesting. There's been a lot of cascading failure analysis out there, but none applied to specifically ocean current energy, which is interesting. So I have a lot of research to go through. I hope I can fit it into 5 minutes. So the main research goal was to create a Python model and model this interdependent network and try to find out what factors could cause a catastrophic failure. So an interdependent network, which is what these arrays would create, this is a best visualization of it. You have one network A, which could be like your power network, and then you have a network B, which could be your communication network, all with different links and nodes within its own, but then you have these dashed line, which are the interdependent links. These interdependent links create a big vulnerability in the system, which means if you start removing a node, you could create not only a failure in network A, but also network B. And so that's the kind of thing, these are the kind of problems we were specifically looking at. We're looking at what problems can create this cascading failure, meaning you take one node out, that's going to make 3 nodes fail. Each of those 3 nodes are going to make 3 more nodes fail, that kind of cascading failure. So we started with a really basic network model. We thought the simplest one would be one anchor, which are the triangles, a simple mooring cable up to I'm not a good artist, I just put these sketches together, just so you can kind of visualize it a little bit. But then the kind of dotted lines at the bottom there connecting the triangles in a grid, those are going to be like your communication and your power systems. And then you have, of course, your mooring cables. So you kind of get an idea where the nodes are and where the edges are in a system. All those anchors and then the turbines themselves are going to be nodes in our network where all of these systems come together and these interdependent links are formed. And then you also see just the edges in each network individually. And so how did we model this failure? Okay, there's lots of different ways to do this. The one that we picked for most of our tests were the simplest failure we could think of. We at random selected a node from any network and just removed it, and then looked at how the results cascaded from there. There are plenty of other things you can do. With ocean current energy, there are mechanical failures, which would be more probable that certain things would fail, so you could put that in your code and say, oh, this would fail before this other thing. You have marine animal interaction where you could just slow down a turbine, so you're not even taking a node out of a network, you're just reducing its capacity. And then you also have commercial disturbances. If a fishing net just ran, not very likely, but if it did go through this array, it could take out multiple nodes. So these are the different kind of failures that we had to consider. And so this big graph right here is just to give you an idea of, this was one independent variable that we tested, which was the maximum load the maximum initial load that a node could start off in a network, and the probability that it would reach catastrophic failure. So you can see the numbers are not important. What you want to look at is just the actual data. It's the threshold at 0.75, and of course the number isn't really important. It's just clear to see that after a certain point, no matter what you do with your system, if the initial load starts off too high, you're going to have catastrophic failure if something happens. So this is something that manufacturers would look at and go, okay, so even if we change our initial data and the numbers at the bottom change, they know that there's going to be a threshold for some of these things that they need to stay under to make sure that they have a reliable and robust system. And not all of our independent variables gave us such a nice graph. We have some like this. We looked at the array size. We changed it from about 3 to 100 different turbines connected, and then ran the simulation again to see what the probability was that you would have catastrophic failure. This is a literal roller coaster of emotions here. So we decided that really what we were looking for is how do different variables affect the probability of catastrophic failure. So, we're not looking at the specific data. We were just interested in getting a model that worked, that gave us some reliable data that showed that we can plug in different factors into our program, our code, and get something that could give manufacturers an idea of what not to do whenever they're building these things. And this research has a lot of potential. I really did the framework for it. I did a lot of the background research and kind of figured out where to go, but this research can continue. We can change the topology, how everything's connected. You can test more, factors for what could create a catastrophic failure. So even though I got the project going, there's still a lot to do. And that concludes this presentation.